Hello everyone. So today let us look into another part, very important part in the stereochemistry is the asymmetric synthesis. Okay. So in this particular video, I'll try to talk about the synthetic aspect of stereochemistry. So if we look at the basic molecules that we find in the nature, we find that there is a lot of asymmetry present in the nature. For example, if you look at this particular example of limonene, okay, and this structure has one particular chiral center present at this particular point, okay. So we have two different enantiomer of limonene given here. One is a plus and one is a minus form. Okay, so what you can see is one of the enantiomer, that is the plus enantiomer of the limonene, is actually giving the smell that you observe in the oranges. Okay, however, the minus limonene is the one that gives the smell of lemons. Okay, so see, just one change in the asymmetric center lead to a drastic change in the property that you come across in your natural products. Here another example is to carbone, okay, which give the smell of spearmint, and another plus isomer give the smell of the other kind of seed. So see, just the enantiomer itself is giving two different properties in nature. Even this particular aldosterone, which is actually plus isomer, is responsible for the stale smell that you sometimes observe in the urine. Okay, so that is coming from the plus enantiomer. However, the minus enantiomer is usually orderless. So see, in the nature what you find is a lot of asymmetry present in the given molecule. Now coming to the drug molecules, okay, so this is an example of L-dopa. It's a very common drug, very largely used drug for treating Parkinson's disease. However, if you see that since we have an asymmetric center here, definitely it has two stereoisomers possible. One is this particular stereoisomer, another is this particular stereoisomer. One is the L form, another is the D form. So you see, one of the enantiomer is used for treatment of Parkinson's disease. However, the other enantiomer is actually toxic in nature. So that means asymmetry has a great significance, that one of the enantiomer can have a very good property, however the other enantiomer can be really toxic as well. Similarly, you have this particular drug, which is citalopram, which is used used as an antidepressant. Okay, however, its enantiomer is not that effective. Again, another drug is darvone, and this is another drug is novrad. These two drugs are enantiomers basically, though they have been given different name. They are just enantiomers, differing in the here you have actually two asymmetric center, one present here, another present here. Similarly, you have here as well as here. These two are enantiomers basically. They are mirror images of each other. However, one of the enantiomer is a painkiller, another is a cough suppressant. Okay, so drug molecules, or apart from the nature, in drug molecules also you see the importance of asymmetry, and that is why study of stereochemistry is very, very important. Here I'll give you one more example. This menthol. Many of the products that you use have menthol used in it, and these days we are using a lot of menthol based paste and different other commodities, right? So you might be thinking every time it is extracted from the plant, but it's not the case, because usually when you do any kind of extraction from the plant, these are always gotten in very small amount. Okay, so that means you cannot use it in a larger scale. Okay, so that means this particular compound is actually synthesized. Okay, and that is why we are able to meet some 30% of the world's supply is not from the plant source, but they are made actually synthetically. And that is why the study of asymmetric synthesis is very, very important. Asymmetric synthesis means the way in which you can synthesize asymmetry in a molecule. Okay, so that particular synthesis is very, very important, because you can see from all these examples that I have discussed with you right now, you see the importance of asymmetry. Just a change in the stereo chemistry at an asymmetric center can drastically change the property that a particular molecule exhibits. So what are all the challenges that you actually face in an asymmetric synthesis? There are two common challenges that you face. One is the formation of a racemic mixture. Another is the phenomenon of racemization. Now what are these? Racemic mixture is like when you carry out a particular synthetic reaction, and if your reactants are achiral, and when you carry out a reaction and it leads to a chiral product. So when you start from an achiral reagent and get back to the chiral product, during the reaction, if you do not have any other outside source that can control the stereochemistry at the new chiral center, then what happens is that it will lead to racemic mixture. So the chiral product will usually give rise to equal amount of the plus isomer and the minus isomer. So when you get such a mixture which contain equal amount of both the enantiomer, we say that we have got what you call as racemic mixture. Now what is racemization? Racemization is basically when you start a reaction with a optically active compound, okay, and then when you do the reaction, it leads to racemization. Racemization means it leads to the formation of both the enantiomers. Suppose you start with one particular optically active compound and you do the reaction, and in the product you see both kind of enantiomer in the product, then we say that that reaction has undergone racemization. Okay, and racemization can be of two types. One is complete racemization, where you get equal amounts of the plus isomer as well as the minus isomer. However, there can be partial racemization, where partially only the other enantiomer is formed. In such cases, you usually exhibit an enantiomeric excess in the reaction mixture, which I'll be talking in another video, where I'll be talking about what do you mean by enantiomeric excess. Now, I'd like to elaborate what do you mean by racemic mixture. What do you mean by the formation of a racemic mixture? Basically, if you are asked what do you mean by racemic mixture is nothing but a mixture which contains equal amounts of the plus isomer as well as the minus isomer. But here, since we are talking about synthetic aspect, I'm saying one of the drawback of asymmetric synthesis is formation of racemic mixture. Now, how that it happens? So I told you, when we start with the achiral molecule, so this particular 2-butanol, okay, this is 2-butanol. This particular molecule is actually achiral because there is no chiral center present in the molecule. Now, if you look at this molecule, basically what is happening is reduction of this carbonyl functional group. So when you reduce it, it is converted to alcohol. So basically hydrogen is added across this double bond, and you get OH and H here. So you got a 2-butanol. Now, once 2-butanol is formed, what you can see is here you have generated a asymmetric center at this carbon center. So you are moving from a achiral molecule to a chiral molecule. So when you do such kind of a reaction, often what happens, if you do not have an external factor which can have an effect on the control over the formation of the chiral compound, then in such cases it often leads to equal amounts of both the enantiomers, that is plus enantiomer as well as the minus enantiomer. So that is why you get here in this case a formation of racemic mixture. Now, if mechanistically you talk about what is happening in the reaction, so basically it's a heterogeneous catalysis. So in this particular case, this gray region represents your nickel surface on which you have your hydrogen molecule, which is kind of adsorbed onto the nickel surface. So when it undergo reduction, okay, you know that this 2-butanol at this particular center of carbon, it's a trigonal planar structure. It's a planar shape. So when the hydrogen molecule add, it can add from this end of the plane as well as from the top end of the plane. So when it add from this end of the plane, it give rise to R enantiomer. And if it add from the opposite side, so in this case they have shown us they can revolve the molecule, so it exactly means if the hydrogen is adding from the other side of the plane, so it give rise to what you called as S enantiomer. So that can be both possible. The hydrogen atoms can add from one side of the plane as well as the other side of the plane. That is why equal possibility of addition of hydrogen from both the ends of the carbonyl. Therefore, you can have both the R as well as S enantiomer formed in this case. Okay. Now that is why whenever you have certain external factor which can control this addition, that means some factor which can hinder the addition on this side of the plane of the carbonyl, then you can say that you can get a good excess of R enantiomer. However, if you do not have any external factor which can control the addition of hydrogen at both the ends of the plane, then it would definitely give rise to a racemic mixture. So that is what is happening in this particular example. Now, racemization. So racemization, I told you, basically it means when you start with the optically active compound and then give rise to another optically active compound, it often leads to certain reactions, often leads to formation of racemization. So here, if you look at this particular reaction, basically it's a nucleophilic substitution reaction. And since water is a weak nucleophile, Br is a good leaving group, therefore this reaction pathway would be more probably SN1. Okay, nucleophilic substitution unimolecular. Okay, so when you have a SN1 mechanism, you know what happens initially. The leaving group leaves and you have a carbocation generated, and this carbocation is sp2 hybridized, so it is planar structure. So once a planar structure of this carbocation is formed, the nucleophile, that is the water, can add from both the sides of the plane, and therefore you can have the formation of both the enantiomer, both the alcohol enantiomer in this particular case. Okay, so such reaction in which the reactant itself is optically active, but it also gives rise to product which is optically active. But since the pathway by which this particular reaction happens seems to be a chiral intermediate, therefore it leads to equal amounts of both the enantiomer, and therefore this particular reaction is a racemization reaction where both the enantiomers are formed. Similarly, you have enolization here. It's a carbonyl compound, so alpha hydrogen can enolize. This is a achiral intermediate, which then again goes back to the ketone stage. It leads to racemization in this particular reaction. So you see, it is a very important drawback. Both the formation of racemic mixture as well as racemization is a drawback in the asymmetric synthesis. So how to solve this problem? So that is what we are going to do in the next video, where we will be talking about the roots of asymmetric synthesis. Thank you very much for your attention.